All right, today we're going to go over balancing chemical equations. So first, chemical equations, what are they? They're used to represent chemical changes, or chemical equations represent chemical changes. In a chemical reaction, a new substance is made. And first of all, we need to know what a chemical formula is. A chemical formula is something it's a formula that represents a compound. So for example, CH4. So if we just stop here, there are two types of numbers on a chemical formula. First type here, this is called a subscript. So a subscript is the number of atoms per molecule. And the second thing we have to know that is if there is no subscript right here, then we assume it's going to be a 1. So in this case, CH4 is what we call methane. And so one molecule of CH4 actually looks like this, where there's 1 carbon and 4 hydrogens around, right? So this is 1 molecule, right, of CH4. We know there's 1 because there's no number in front, which we call the coefficient. So this tells you the number of molecules. So that tells you the number of molecules, that's a coefficient. And then there's a subscript. Here I have a second example. So 3Na2O would just be, if we were to write it out, the Na, and O, that's 1, Na, NaO. This is an ionic compound, right? So there's 3 of them. Remember that Na has +1, and these have a -2, so together. Okay, and so there's 3 of them. So there's 3 molecules. How do we know there's 3 molecules? Because the coefficient is 3. There's 2 sodiums and 1 oxygen per molecule. How do you know that? Because that's they tell you by the subscript. Here's your basic chemical equation. This is what we call the decomposition of hydrogen peroxide. We have the reactants on the left, products on the right. In the middle is called a yield sign. So that arrow here is the yields. And then the other piece of information you can get from the equation, the chemical equation, is the state of matter. So this L means it's liquid, and then this G here means it's a gas. And so there are 4 different symbols, I guess we can, or abbreviations. We can have a liquid, solid, gas, or aqueous. All right, so before we get into full-blown equations, we have what we call skeleton equations. And these are equations that only show reactants, products, and their physical states only. They're not balanced. For example, here's a skeleton equation, so let's read it. It says magnesium reacts with oxygen gas and solid magnesium oxide is formed. All right, so from this, we're going to create what we call a skeleton equation. So it says right here, magnesium reacts with oxygen gas and solid magnesium oxide is formed. So right now, if I were to diagram this, these are my reactants because it says magnesium reacts with oxygen gas. And then my products is solid magnesium oxide. That's my products. Why? Because it says solid magnesium oxide is formed. Formed is another word for produced or made or react, something like that, right? And so I have So if I write out this equation to be magnesium plus oxygen gas yields magnesium oxide. All right, now let's put that into our chemical formulas. Magnesium is just Mg. Now I got to check to myself. Is magnesium a diatomic? No, magnesium is not diatomic, so it's just going to be Mg by itself. Oxygen gas. Is oxygen gas a diatomic? Oxygen is a diatomic, right? Hofbrinkel. So O2. And then what is magnesium oxide? So magnesium oxide is Mg with O, right? Magnesium, I'm going to do this off to the side. So So this is where last chapter is important. You have to be able to translate magnesium oxide. Well, magnesium is Mg plus 2, right? Oxygen is O minus 2. So isn't it a 1-to-1 ratio? They neutralize each other. So it'd just be MgO. So I've now translated basically this sentence into a skeleton equation. It's not balanced right now, but that's okay. We just wanted a skeleton equation. Okay? All right. Let's go ahead and actually now start balancing chemical equations. So we've talked about how balancing chemical equations have to follow the law of conservation of mass. So let's do an example. Here's the big rule here, though. So before we start, you can change coefficients, meaning you can change the number of molecules there are, but you cannot change subscripts. I'm going to write this a little bigger. This is my chemical equation here. Now, this is unbalanced, and I'll show you why. Each element should have the same number of atoms on each side, on the reactant and product side. So if you look here, the one that's unbalanced is oxygen. Here I have 2 oxygens on my reactant side and 2 on my product, or 1 on my product, right? And so it's unbalanced. All right, so what can we do? Well, this is what I'm going to do first. H2 is H. I draw it out. Over time, though, and oxygen is OO. And then this is HHO, right? 2 H's and 1 O, H2O. I draw a line in the middle. First, I ask myself, now, when balancing, it's always best to leave oxygen, hydrogen. You want to balance oxygen and hydrogen last. But in this case, we have hydrogen and oxygen, so it doesn't really matter. If you look, my hydrogens are balanced, right? I have 2 hydrogen on this side, 2 hydrogen on that side. So I'm good. But my oxygens aren't balanced. Remember, though, what I can't do is I can't just be like this. And the reason is because this reaction creates water. So it doesn't create hydrogen peroxide. Like, it just doesn't. This is what the reaction is. So you can never add a subscript. But what you can do is you can add more water. So let me add a second water, right? Now my oxygens are balanced, but what you see is, my hydrogens aren't balanced, so I can go to this side and add more hydrogen, right? Now, I can't add one hydrogen, I have to add both, right? Because H2 is the molecule that is reacted there, okay? So you just can't add like another H. So in this case, if you look here, I have 1, 2, right? I have 2 molecules of hydrogen gas. So I'm going to put a 2 there. I have 1 of O, so I'm going to leave it blank. Remember, if it's blank, you assume that it's going to be a 1 there, right? And then I have 2 waters, so I put 2. So my balance is 2H2O plus O2 plus 2H2O. Shorthand, we just write 2, 1, 2, right? What we mean by that is that the coefficients in order is 2, 1, 2. So that the answer is 2, 1, 2 here. Okay? All right. So I have a couple more for you to try. You can try this on your own, and then I can show you the answer. So K2O plus H2O is KOH. So this is, oops, let me go back. Right? So remember, I'm always going to leave hydrogen and oxygen last. I have 2 Ks on this side, right? And I have 1 K, 1 potassium, so I'm going to change that up. So now my potassiums are balanced, and then I'm going to look at my oxygen and hydrogen next. I have 2 oxygens right here, 2 on this side, so I'm good. I have 2 hydrogens here, 2 hydrogens on this side. So it's pretty easy. I only have 1, so I'm going to leave that blank. 1 here, and then 2. So the answer is 1, 1, 2 here. The next one I gave because I wanted to show you a little trick here. And the trick is, if you see a polyatomic, so how many Cls will have 3 Cls? So I put that there, NH4OH. Now, if you remember, NH4 is a polyatomic, so I'm going to keep it together. I'm not going to write out 4H. And then OH is a polyatomic, so I'm going to keep it together. Just think of them as one whole thing. So NH4 is one whole thing, OH is one whole thing. Here's Fe, and then OH3, so OH, OH, OH. But I'm going to keep them together. And then NH4 is NH4Cl. So I'm going to kind of see if I can make it easier. So OH, OH, OH is 3, and then hopefully that'll help me. All right, so let's take a look. Remember, always leave oxygen and hydrogen last. So I'm going to look at my ions. Right now my ions are balanced. I have one Fe on one side, one Fe on the other. My chlorines, though, aren't balanced. So I'm going to I need 3 chlorines, which means I'm going to need 2 more of this. Right? So now my chlorines are balanced. My ions are still balanced. And then I'm going to look at my NH4. Remember, NH4 is ammonia, and remember, we're going to keep them together, right? So NH4, if you see, I have 3 on this side here. So I need 3 on this side, so I'm going to add 3 more of these. Remember, we got to add the whole thing, right? The whole molecule. And if you look, the OH is balanced out. Here's OH, 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 and then here's 3 OHs. So it ends up being, this will be 1, this will be 3, this will be 1, and this will be 3. So the answer is 1, 3, 1, 3. Okay. Next one, you see polyatomics. Keep those OHs together. So Al, so 1 OH, 2 OH, 3 OH. And this is H2SO4, so HHSO4. I'm going to keep SO4 together. This is Al, Al, SO4, SO4, SO4. And then this is H2O, so plus H2O, so H2. Okay, so that's what I got. Remember, let's leave the hydrogens towards the end. My aluminums aren't balanced, so I'm going to need a second aluminum here, right? What else do I need to check? Are my SO4s balanced? My SO4s are not balanced, so okay, so now my aluminums and SO4s are balanced. Let's see what kind of mess I got myself into here. So, let's take a look. Let me count up my OHs here. So I have 1 OH, 1 OH, 1. So what I wanted to show you is within this hydrogen, within this water here, you actually have an OH. And so you need 6 of these. So it's 1, 2, all right. So here's 6 OHs. And then what about my hydrogen? So I got 1, 2, 3, 4, 5, 6, and I have 6 here that I've unaccounted for. Okay, that was a tough one. So what do I have? I should have 2, 3, 1 here, and then 6. All right. All right. So this is kind of the ultimate here. Now I'm going to have you actually, what you'll do is you'll convert this into an actual chemical equation, and you'll balance it. So you'll first have it as it'll first start as a skeleton equation. So solid sodium reacts with chlorine gas. Boom. There's my reactants. And it forms, what does it form? It forms solid sodium chloride. So here's solid sodium. It's solid, so I'm going to put a little S there. Reacts with chlorine gas. Chlorine's actually a diatomic, and it's a gas. It forms solid sodium chloride, NaCl. Sodium chloride, remember, Na plus, Cl minus, right? Oops, I don't want to put a plus there. And then we know it's solid. All right, now let's balance this, right? So you have NaCl, 2 chlorines. and 1 Na. And so I need 2 chlorine, so I put a second molecule there. I need a second sodium, so it should be 2, 1, 2, right? All right, the next one. So solid potassium metal reacts with water to form. So it reacts with water. Okay, that's my reactant. So potassium solid. Metal reacts with water. Water is liquid at room temperature to form potassium hydroxide solution. So this is actually tricky. Potassium hydroxide solution, whenever you see solution, then that means the word aqueous. Potassium hydroxide is K plus 1 and OH minus 1. So this will give you KOH. It's solution, so it's what we call aqueous, or in water, plus hydrogen gas. Remember, hydrogen is diatomic. This is my equation, okay? All right, so let's take a look. We have K, we have H, HO, we have KOH, and then... All right, so my potassium's good. My oxygens are actually balanced, but my hydrogens are not. Now, it's a little trickier, but if you look on the reactant side, I have two H's, right? So I'm never going to get an odd number of hydrogen. It's impossible, right? Because there's always going to be 2 hydrogens. Any multiple of 2 is going to be even. But here I have 3 hydrogens, if you look here. So I have to actually make this even. The only way to make this even is to actually double up, right? Now it's even. I have 4 hydrogens. And what I can do is actually just do that. So if you count it up, I have 2 oxygens on both sides, 4 oxygens on both sides, and 2 potassiums now. So the final will be 2, 2, 2, and 1. Okay? Kind of like a puzzle almost. The only way to get better at this is just practice. So here's practice, and I put a key up there for you as well. Okay?